A toothpaste brand claims their product will destroy more plaque than any product ever made. A politician tells you their plan will create the most jobs. We're so used to hearing these kinds of exaggerations in advertising and politics that we might not even bat an eye. But what about when the claim is accompanied by a graph? After all, a graph isn't an opinion. It represents cold, hard numbers, and who can argue with those? Yet, as it turns out, there are plenty of ways graphs can mislead and outright manipulate. Here are some things to look out for. In this 1992 ad, Chevy claimed to make the most reliable trucks in America using this graph. Not only does it show that 98% of all Chevy trucks sold in the last 10 years are still on the road, but it looks like they're twice as dependable as Toyota trucks. That is, until you take a closer look at the numbers on the left and see that the figure for Toyota is about 96.5%. The scale only goes between 95 and 100%. If it went from 0 to 100, it would look like this. This is one of the most common ways graphs misrepresent data, by distorting the scale. Zooming in on a small portion of the y-axis exaggerates a barely detectable difference between the things being compared. And it's especially misleading with bar graphs, since we assume the difference in the size of the bars is proportional to the values. But the scale can also be distorted along the x-axis, usually in line graphs showing something changing over time. This chart showing the rise in American unemployment from 2008 to 2010 manipulates the x-axis in two ways. First of all, the scale is inconsistent, compressing the 15-month span after March 2009 to look shorter than the preceding 6 months. Using more consistent data points gives a different picture, with job losses tapering off by the end of 2009. And if you wonder why they were increasing in the first place, the timeline starts immediately after the US's biggest financial collapse since the Great Depression. These techniques are known as cherry picking. A time range can be carefully chosen to exclude the impact of a major event right outside it, and picking specific data points can hide important changes in between. Even when there's nothing wrong with the graph itself, leaving out relevant data can give a misleading impression. This chart of how many people watch the Super Bowl each year makes it look like the event's popularity is exploding, but it's not accounting for population growth. The ratings have actually held steady because while the number of football fans has increased, their share of overall viewership has not. Finally, a graph can't tell you much if you don't know the full significance of what's being presented. Both of the following graphs use the same ocean temperature data from the National Centers for Environmental Information. So why do they seem to give opposite impressions? The first graph plots the average annual ocean temperature from 1880 to 2016, making the change look insignificant. But in fact, a rise of even half a degree Celsius can cause massive ecological disruption. This is why the second graph, which shows the average temperature variation each year, is far more significant. When they're used well, graphs can help us intuitively grasp complex data. But as visual software has enabled more usage of graphs throughout all media, it's also made them easier to use in a careless or dishonest way. So the next time you see a graph, don't be swayed by the lines and curves. Look at the labels, the numbers, the scale, and the context, and ask what story the picture is trying to tell.
In this video, I'm going to be teaching you all about skewed and symmetric distributions and how we can locate the mean, median, and mode with ease.
Here we have a bell curve. This curve is considered symmetric, which means that each side is the mirror image of the other. You'll see that in the center, I've identified that this is where the mean, median, and mode of the dataset lies. When you're looking at a curve, it's always easiest to identify where the mode lies first. The mode's just the most repeated value, so it's always going to be where the hump or the peak of the curve is. When we take a look at the mean, we need to think of it as a set of scales. And when we think of it as a set of scales, we need to try and balance out the distribution. Because this curve's symmetric, the mean lies right in the middle, as it's the same amount of weight on each side of the bell, or if you think of it, on each side of the scale. The median's just the middle value of the data set, where half the values lie above the median and the other half of the values lie below the median. So the median will also lie in the centre of this distribution. Let's now go and take a look at a couple of skewed distributions. This is basically when we have some extreme values in our data set which pull our curve to the right or to the left. What we're looking at here is a positively skewed distribution. You might also call it a right skewed distribution. We call it a positively skewed distribution or a right skewed distribution because this tail here points in the positive direction or in the right direction. This is where we have some really extreme values being pulled to the right. So this is where we have some really high data points. For example, we can think about this as the cost of a house. Most houses lie in the hundreds of thousands of dollars, whereas the ones down here on the right end or the right tail here are really the houses that are in the millions and even tens or hundreds of millions of dollars right up the far end. So there are less houses that cost in the millions and many more houses that cost in the hundreds of thousands of dollars range. Now, when we take a look at where the mean, median and mode lie in this type of distribution, things are going to change a little. You'll see that our peak is further to the left here. This is where our mode lies, as it's right where the peak of the distribution is, so the most frequently occurring number. Okay, and the mean, where would the mean lie? Well, the average, which is just the mean, as it's just the average of a set of numbers, is going to be dragged toward the tail. So the mean's going to be dragged in the positive direction. You could think about this as a set of test scores. One student in the class might score 80%, another might score 60%, and another student might only score 10%. If we were to average that out, our class average would be 50% for the test. However, if we had an increase in one of the scores, the final score, so we've got 80%, 60%, and if the final score went up to 75%, that brings our class average to 70%. So you can see that if we're increasing numbers in our data set, our mean is going to increase as well. So if we go back up here, let's put our mean, I'm going to exaggerate it a little bit here, but we'll pop our mean here, as it's going to be pulled in the direction of the extreme values. The median doesn't move as easily as the mean. It's not as affected by extreme values because all the median is the middle value of any data set. So if there are extra values in the tail end, the median's only going to be pushed just a little. So we can essentially pop the median in between the mode and the mean. So in this skewed distribution, we have the mode, where the peak of the distribution is. The mean is always toward the tail end. The median is always pulled slightly toward the tail, but is not as affected as the mean. So it sits between the mean and the mode. Let's quickly take a look at a negatively skewed distribution. So we have the bulk of our data in here, and then some extreme values that pull our data set this way, which is why this tail is created moving in the negative direction. To identify our mean, median, and mode, we always pop the mode at the peak. So here is our mode, the peak of any distribution. Recall that our mean is going to be pulled in the direction of the tail, so let's just pop our mean roughly here. Our median is less affected by the extreme low values in this case, so it still moves in the same direction as the tail, but it's not as exaggerated as the mean.
This is a normal distribution, or a bell curve. On the x-axis, we have the scores. On the y-axis, we have frequencies. Frequencies are how often a score occurs. It might help to visualize with something like an IQ. Here, the mean IQ is 100. Now we're going to look at deviations. So here we have one standard deviation. For our IQ, one standard deviation above the mean would be 115. 85, however, would be one standard deviation below the mean. We see that 68% of the population will fall between one standard deviation above the mean, one standard deviation below the mean. Next, we see that 95% of the population will fall with two standard deviations above the mean or two standard deviations below the mean. Next, we see that 99.7% of the population fall between three standard deviations above the mean and three standard deviations below the mean. We have the 68, 95, and 99.7 rule. That means that 68% of the population is going to fall between one standard deviation below and one standard deviation above the mean. 95% of the population will fall from two standard deviations below to two standard deviations above the mean, and 99.7% are going to fall from three standard deviations below the mean to three standard deviations above the mean.
Now, the best way to understand the differences between descriptive statistics and inferential statistics is to go through an example. All right, so the idea is that descriptive statistics talks about a sample, and an inferential statistic is a statistic that is applied to a population. So let me explain what the difference is between the two. So here, let's say we have a huge population. We have tons of people, right? This is our population, and inside our population, there's just a bunch of people, or maybe a bunch of plants or something. And then a sample is just a portion of that. So we're going to blow up this image and get a better understanding of that sample. So in this example, we have our population, and we took a sample from that population. Now, let's say we measure an attribute of that sample. Let's say we measure that 52% are Republicans. Now, at this point, this statistic is a descriptive statistic in the sense that this 52% is talking about this sample here. We're specifically focused on the sample. At this point, we don't need the population. We're strictly focused on the sample. So this is called a descriptive statistic. Now, if we were to be interested in maybe talking about this group, we might say something like, this is that 52% of this population are Republicans. Now, in this case, the 52% is represented as an inferential statistic, simply because we're making an inference from that statistic. We're assuming that this thing right here, this 52%, can project onto the population there. And that might be true, that might not be. It really depends on whether or not your sample is biased, whether or not you have a good representation of the population. But the idea is, if we are strictly focused on the sample, if we ignore the population, then it is called a descriptive statistic. And if we focus on how we can use this statistic as a measure of inferring about the population, then we would call that an inferential statistic. So again, I just want to really recap this one more time. The idea is that if you have a sample and you just focus on that sample, you just really want to talk about that sample. You don't care about population. You don't really care about making inferences about other people. You just want to focus on this group of people that you analyzed. If that's the case, then it's called a descriptive statistic. It's describing the sample that you measured. But if you start taking that and you project that onto a bigger group, like a population, that statistic becomes inferential statistics, in which case you're making inferences about a population. You're basically guesstimating facts about the population. And so those are the two differences.
If you've ever seen a news story about a scientific study, you've probably heard something like statistically significant results. More likely than not, what this is referring to is a scientific study that found something like p is less than 0.05. In this video, I'm going to do two things. First, I'm going to explain what it means when someone says something like statistically significant result. Then I'll give you an intuitive explanation of what those p-values are, and finally, if you stick around to the end of this video, I'm going to explain why we use a threshold of 0.05 and not say 0.04 or 0.08 or 0.15 or anything else when determining statistical significance. So let's start with what statistical significance is. In the scientific world, a key idea is that we can never prove something to be true. That seems like a pretty strange thing to say, since it sure seems like all that science is concerned with is proving things. The Earth is round, the sky is blue, gravity attracts objects together. It sure seems like those are all proven to be true, and yet they're actually not. Instead, what science does is provide evidence that something isn't true. This is a pretty subtle distinction, but it's basically the whole point of statistical significance testing. So let's unpack it. Most likely, you believe that if I drop this ball, it will fall to the ground. I bet you're willing to go a step further and say that, assuming I don't do anything to trick you, this is always going to be true. In other words, no matter what, when I drop this ball, it'll fall to the ground. The problem, though, is that we can't ever test that last idea, that this will always happen. Always is a pretty long time, and to show that something always happens, you need to observe an outcome in every single possible condition that could exist across all of time. You really can't prove to me that 100 years from now this ball will still fall down when I drop it. I mean, it probably will, but you can't prove it. Instead, let's see what you can do. You can think about the opposite case and make the prediction that if I drop this ball, it will not fall to the ground. So when I do drop it and it falls, we just provided evidence against the idea that a drop ball always stays in place. And we can repeat this a bunch of times if we want to provide even more evidence against the idea that the dropped balls always stay in place. No surprise, the ball keeps dropping, and the evidence against the idea that a drop ball always stays in place keeps mounting. At some point, we feel pretty confident saying that we reject the idea that a drop ball always stays in place. Note that we didn't prove that a drop ball always falls to the ground. That we can't do. Instead, we can disprove the idea that a drop ball always stays in place, which sure seems like me saying that a drop ball always falls down, but that's not the case. We don't have evidence to prove that drop balls always fall down. We've only observed that a few times, and who knows what will change in the future. So what does this have to do with statistical significance? When I say that something is statistically significant, I'm comparing the result of some kind of analysis to what is called a null hypothesis. A good analogy to help understand what a null hypothesis is a jury looking to convict a defendant or not. Our legal system uses the idea of innocence until proven guilty. With statistics, that innocence is the null hypothesis. It's the idea we assume to be true until evidence is presented to show us that it's not. For a jury, that evidence might be DNA at the scene of a crime or eyewitness testimony. With enough evidence, the jury rejects the idea of innocence. For statistics, think of our ball dropping example. If you know nothing about how the world works, and make a prediction that dropped balls never fall, that would be your null hypothesis. And when you see that the ball really does drop, that would be the evidence you use to reject that null hypothesis and conclude that dropped balls don't always stay in place. If we're testing if a drug is effective at reducing heart disease, our null hypothesis is that the drug is not effective. If after conducting a randomized experiment, we find that the drug reduces heart disease by some meaningful amount, we can reject the null hypothesis that the drug is not effective. Note that we haven't proven that the drug is effective because we haven't tested it in every single conceivable case, just in our single experiment. Instead, we've provided evidence to reject the null hypothesis that the drug is not effective. The more experiments we run that show that the drug is effective at reducing heart disease, the more our confidence grows. We can never get to the point where we are certain that the drug reduces heart disease, but we can get close enough where practically we can start prescribing the drug. So when you see something reporting a statistically significant result, what they really mean is that there was enough evidence provided to reject a null hypothesis. But how much evidence do you need to do that? That's where that p is less than 0.05 comes in. 0.05 is a cutoff. It's something we compare a statistical result to determine if we have what is typically called a statistically significant result. Without getting into the weeds on different statistical tests, whenever you conduct one, there is a corresponding p-value. The smaller the p-value, the greater confidence you have in rejecting whatever the null hypothesis is. So let's say we are comparing the efficacy of that heart disease drug from before to a control group that didn't get the drug, and we found that fewer people suffered from heart disease after taking the drug compared to those who didn't take it. We might find a relatively small difference between these two groups and get a p-value for that comparison of 0.60, which is well above our cutoff of 0.05. That would mean that the difference in heart disease across our two groups was so small that we don't have enough confidence to reject the null hypothesis that the drug doesn't work. In another case, we might see a large difference in heart disease across the two groups and get a p-value of, say, 0.01, which is less than 0.05, so we say that we do have enough evidence to reject the null hypothesis that the drug doesn't work. In that case, we start to build confidence that the drug is effective. Getting a bit more precise though, that p-value has a very specific meaning. Let's take the case from before of a p-value of 0.01. This means that if the null hypothesis were true, if the drug really doesn't work at all, the chances of us getting the result that we did, or one even stronger, is only 1%. In other words, given what we observed, the much more likely case is that the null hypothesis is actually false. It would be incredibly unusual for us to find this result if the drug really didn't work at all. On the other hand, if our p-value from that drug trial was that higher value of 0.60, that means that if our null hypothesis were true, the chance of us getting the result that we did is a whopping 60%. In other words, it's very likely that the null hypothesis is, in fact, true, because we'd expect to see this result 60% of the time, even when the drug does nothing at all. So as p-values get smaller, we increase our confidence in rejecting the null hypothesis. Bringing back that p is less than 0.05 idea, basically that says that the convention that many scientific disciplines follow is that to have enough evidence to reject a null hypothesis, your result needs to be no more than 5% unlikely if the null hypothesis is actually true. Any more than that, and we say we don't have enough evidence to reject a null hypothesis. And any less than that, and we say we do. Which brings us to the final point. Why 0.05? As in, why is the cutoff for whether something is statistically significant or not 0.05? Why not 0.20 or 0.01? The answer is actually simple. It's totally arbitrary. Someone at some point in history, probably a man named Ronald Fisher back in the early 20th century, decided that 5% was the value. And we've stuck with it ever since. There's really no good reason for 5% to be the cutoff for statistical significance. It's just a convention. If you want to be sure that your evidence is very strong in its ability to reject a null hypothesis, pick a smaller cutoff like 0.01. If you don't care as much about strong evidence, pick a higher value like 0.15. It actually doesn't matter. There's no right answer. 0.05 as a cutoff is just a convention we all agree to use, but it doesn't make it right. In fact, there are plenty of people who argue that we should throw away this whole idea of statistical significance testing, and instead focus on things like confidence intervals, Bayesian estimates, and effect sizes. In some ways, those people are right. On the other hand, conventions help us have a common language about things like evidence. When we have a shared language about science, we can communicate better, and that allows knowledge to grow.
I am going to die eventually, which is pretty important to me personally, so I'd like to know roughly at what age I am most likely to die. You might guess something like 70, which based on a national data set was the average age of death in the US for men who died between 2018 and 2023. But it might be that 79 is the more accurate answer, which is an extra 9 years. So how can I make sure I'm using the best number to answer my question? Can stats really tell me when I might die? And is there a way to look at these numbers and not have an existential crisis? Statistics are vital for so much of what goes on around us, from designing video games to creating impactful government health policies. But statistics can be misleading. It's not because the numbers are lying. It's that if we don't understand how the numbers are being used, we might get the wrong impression about their meaning. Scientists use statistics to understand data, but when they're looking at those numbers, they have all of the context that goes along with them. By the time these stats are reported on in the news, they often lose some of that context, which can have big impacts on the ways that we see the world. Scientists rely on numbers to build knowledge. But since they can't measure every person, they use samples. Smaller groups they can measure to better understand a larger group, which means there's always some uncertainty. So while stats could never tell me, Hank Green, exactly when I will die, they can tell me when a person like me is most likely to die. So, what is the typical age of death for an American man? Well, when it comes to statistics, there's a few different ways of determining what's typical. One of the most common is to find the mean, or average, the sum of all of the numbers in a sample divided by how many numbers are in that sample. That's where we get the first number from. Based on a large sample of residents who died between 2018 and 2023, the average or mean age of death of a man in the US is 70. But That mean is dragged down by people who died way younger than 70, even though there are fewer of them. So maybe I don't actually want the average. Maybe instead I want to know the most common age of death, or the mode. That answer is actually way different from the mean. The mode is the number that shows up the most in the data, which is where we get 79 from. But actually, most of the numbers in the sample are to the left of the mode, so it's actually more likely that I'd land on one of the numbers under 79 than that I'd land squarely on or after 79. So say then I want to find an age somewhat close to the average age when someone like me would die. I can look at the numbers in the graph and find the standard deviation, which tells me how spread out the other points in the sample are from the mean, which in turn can help me figure out how typical that number really is. If the standard deviation is small, that tells me most people in the sample are dying at ages pretty close to the average age. Another number that might be helpful is the median, or the point right in the middle of the group, where an equal number of US men die before and after, and that would be 73, still relatively close to 70 and 79, but different enough to matter. Because the median is always the number directly in the middle of the dataset, it is less likely to be skewed one way or the other the way a mean might be, so it might tell me way more about when American men tend to die. Though of course, it still cannot tell me when I'll die. The point is, averages like mean, median, and mode are different ways of telling you what might be typical, but they're way more useful when you understand how each one operates differently. And they're even more useful when combined with the standard deviation, which tells us how typical really is. There's always a degree of uncertainty when it comes to statistics. So another useful question is, okay, but how certain are we of these stats? For a stat to really mean anything, I need to know how much confidence to have in it. How likely is it that if I ran the numbers again, I'd get those same results? For that, I'd need to calculate a confidence interval, or a range of numbers that I can expect a result to fall within a certain percentage of the time. A 95% confidence interval means that if scientists repeated the study 100 times with new samples, the statistic they're measuring would fall in that range about 95 times. It shows how much that number might vary and how much trust can be put into it. A stat with a high confidence interval is quite predictive, but it is not perfect. So when encountering statistics in the real world, it's good to remember that every stat actually has two pieces. First, the number, and second, how precisely scientists know that number. And it is way better to be roughly right than precisely wrong.
Did you know that women also die?
Yes, I did sadly know that.
Well, you just talk about dudes a lot. For example, consider this updated birth control pill. According to the news, it raised the risk of developing deadly blood clots by 100%.
That's definitely a big statistic.
It sounds like it, right? With the old pill, 1 in 7,000 people were at risk of developing blood clots. With the new pill, the risk doubled. Do you know what it became?
Yeah, if it doubled, I'd guess it went from 1 to 2.
What a great guess. It sounds like a lot when someone says risk has increased by 100%, but that's just what scientists call the relative risk, or how much the likelihood of something happening gets bigger or smaller relative to something else, which can be helpful to know, but it doesn't tell us the whole story. For that, we need the absolute risk, or the number of people actually experiencing an event in relation to the population at risk.
The absolute risk stayed relatively low.
Right, it increased to 2 in 7,000. Still important, but people need that context you talked about earlier to make informed decisions. At the time, though, a lot of people only learned about this risk in relative terms through the news. So people switch to less effective pregnancy prevention methods. And you know what poses a higher risk of life-threatening blood clots than the birth control pill? Pregnancy! So the more we understand numbers in context, the better we'll be at making informed decisions for our lives.
Understanding the difference between absolute risk and relative risk can help us make sense of so many of the stats we encounter in our daily lives. Like, how great is my risk of developing cancer if I go to the beach every day and don't wear sunscreen? Which actually brings me to my next point. Scientists often analyze relationships in data, like the relationship between sunscreen and skin cancer. These are known as correlations. A correlation is a relationship between two or more variables, which are basically anything that can be measured or counted. A correlation between two variables can be loose or it can be tight, which we quantify with their R value. It's a number from -1 to 1 that shows how tightly two things move together. 1 means a perfect match, -1 means perfect opposite, and 0 means no connection. The simplest kind of correlation is linear between just two variables. A correlation can be negative, meaning one variable gets smaller as the other gets bigger. Like, for example, how higher rates of wearing sunscreen correlate to lower rates of skin cancer. Or it can be positive, like if, say, higher rates of ice cream sales correlate to higher rates of shark attacks. You might have heard the saying, correlation doesn't equal causation, but there's actually more to it than that. Like in the case of sunscreen, there's a lot of good evidence that wearing it really does lower the risk of cancer. There is a causal link in the correlation. But in the case of shark attacks, it's safe to say that the ice cream isn't causing them. Warm weather is indirectly leading to both. In this case, weather is a confounding variable, or a factor that influences the outcome of a study without being controlled for. These can blur what's actually going on in the data if scientists don't measure and account for them. For example, some studies have shown a positive correlation between personal health and visits to the beach. But it's hard to know if beaches make people healthier, if healthy people are more likely to go to the beach, or if there's some third confounding variable, like the level of wealth, that results in both better health and more beach visits. And even if scientists do a good job of controlling for all of these variables, they still have to ask, is it possible this result was just a fluke in our data? In other words, was it statistically significant? Statistical significance means the result is strong enough that it would be surprising to get by random chance. But don't let this phrasing mislead you either. In science, significant doesn't mean important. Like how I say, Doritos are a significant part of my life. That means they're important to me. But that's different from statistical significance. Statistical significance doesn't even necessarily mean meaningful in the real world. It's more like it would be surprising to get this result at random, so we should dig deeper. And digging deeper is something we can all do when it comes to statistics. And that begins by understanding that there will always be some uncertainty. Scientists can't possibly measure every version of everything they want to study, but stats can help them measure the uncertainty. And understanding what numbers can and can't tell us about ourselves, each other, and the world can help us not only better understand the way that science works, but also help us make more informed judgments about our own lives.